Okay. Welcome to lecture 23. We will going to enter the last phase of the course. We'll start a new topic on multiplicity codes. Just a reminder, the fourth problem set will be out by the end of the day, due in 2 weeks from now. So in December 5th. Classes there'll be only 4 more lectures, including today. That's today, Tuesday, today, Wednesday, next Monday, next Wednesday. Those who are taking the presentation, or going the presentation route for the final exam, the presentations will be on the following Friday, the week of December 5th, the Friday of December 5th. Those who are taking the exams will be the next Monday, which will be 12th, I believe. But so those who are taking the course for qualifiers have to go the exam route. The others you get to choose between the two. If you're choosing a project, it's better you do it at the earliest. Those papers are not easy. It's going to take a while to look at those papers.
Can anyone see?
Huh?
Can anyone see?
We'll have to figure out how to do this.
Okay.
Yeah, we'll have to figure out how to do this because the last day for exams was 14th. I'm not going to move things around.
No, I don't think so.
Yeah, but even the presentation, right, it's still the. Well, yeah, we'll talk about this. Yeah. Okay. So let's get started. So, thing is, we've seen we've seen the Reed-Solomon code and the Reed-Muller code, which are the 2 polynomial-based codes that we've seen. The Reed-Solomon code, especially, was a code that met the singleton bound. It had amazing properties and it delivered a lot. We saw a lot of nice consequences of the Reed-Solomon code. Similarly, the Reed-Muller code, which also had some very nice properties that had this local decoding feature and other stuff. But there are in some aspects, they both fell short of certain things. Firstly, Reed-Solomon, it is still not known. We were able to list decode it well beyond the unique decoding radius. We were able to list decode it all the way to the Johnson radius. Question is that the end, or can we list decode even more? What we did show, existentially, we showed that there exist codes that are list decodable all the way up to capacity, all the way up to the distance. Question is, do we have explicit codes? So typically, whenever we had such a problem, Reed-Solomon came and said, there's some slight modification of mean that achieves it. And here we were not able to. It only went all the way up to the Johnson radius. It's still open. It's not the case that we don't. It's not true that it doesn't go beyond the Johnson radius. We don't know whether it goes or not. It's still an open question. But here it's actually a tricky case in the sense that it depends on the set of evaluation points. So Reed-Solomon, we defined it very generally with respect to any set of evaluation points, and all our results held good in that very general framework. But we know that there are certain set of evaluation points for which it does not go well. You cannot list decode it well beyond so for certain points beyond the Johnson radius. We also know that there are certain other evaluation points for which it is list decodable, though not efficiently, all the way up the distance. So we do know of these results. What I would like to get is an explicit code. And this was in the context of list decoding. Similarly, in local decoding, we wanted to get codes which are locally decodable, which have rates approaching to 1. Reed-Muller gave you some answer, but they will never get rate better than half. So the question is, can we do? Basic question is there a more powerful code? A more powerful code. And the answer to that, we're going to indeed say, yes, there is going to be a more powerful code. It will be the multiplicity code, the topic of our discussion for the next possibly 3 to 4 lectures. So it will be a more powerful code. I promised earlier, the Reed-Solomon code will be the one code to rule them all. It will actually be the multiplicity code, which will be the one code to rule them all and to bring them all in. So what we will do in the next few lectures is to actually, what we'll do in this lecture is give a formal treatment of multiplicity codes and then see the magic it weaves over the next few lectures. So if you want to continue the LOP or analogy, we will forge the code today, or actually the code was originally forged in the smithy of firstly Kopati, Shubhangi Saraf, and Sergei Yakin. What we will do is recreate the aura and sit back and watch the power of the code over the next few weeks. Okay. So let's get started. So let's recall. What was Reed-Solomon, the two polynomial based codes that we have. We had Reed-Solomon codes and its multivariate analog, which was the Reed-Muller codes. And in both these, how did it work? So let's sort of recall how did the evaluation go. We viewed the message, we interpreted the message, it was some symbols from a field, we interpreted it as giving the coefficient of a polynomial. So the first step was message as coefficients of some polynomial. So the message basically specifies the polynomial. And then what was the code word? The code word was just the evaluation of this polynomial over a particular choice of evaluation points. So this is how we obtained Reed-Solomon as well as Reed-Muller. It was just the evaluation of the polynomial over a specific set of points. In the case of Reed-Solomon, this could, what we've seen, it could be typically an arbitrary set of points. Sometimes we work with SQ or SQ star, but it could, most of our things work for an arbitrary set of points. For Reed-Muller, typically these are product grids. We could work over the entire SQPM, but the product grids were what will come there. An equivalent way of say evaluation set of points, say S, which is alpha 1 up to alpha n, and this is a subset of SQ. M is 1 for the Reed-Solomon, so you have a bunch of points alpha 1. And an equivalent way of taking this is so the code could be viewed as giving P of alpha for alpha in S. That's the code. Equivalently, I could also view this as giving P of X mod X minus alpha over alpha. That's an equivalent. This is exactly the same thing. When you divide this by X minus alpha, the remainder will exactly be P of alpha, because this is the P of alpha, these both are exactly the same. What we'll do is we'll continue this analogy. We'll sort of try to build one. What we will do is not just give the multiplicity code. Both univariate and multivariate. Yeah. Will also be evaluation, but we will not just give the evaluation of the polynomial, we'll also give the evaluation of several derivatives associated. So the evaluation of polynomial and low order derivatives. At a specific set of evaluation. It will be the same thing. In particular, what we give is there will be a set of evaluation points S. We'll give P of alpha, we'll give P prime of alpha, P double prime of alpha, and so on. This makes, and while writing this, assuming it's univariate, you'll have to write different derivatives if you're writing multivariate. We'll all make all of this formal shortly. So that's what I mean. I'm going to give this tuple up to some sort of derivative. Or equivalently, this will be the same as giving P of X. But this will be the same as giving P of X mod If you want to give all the way up to the S order derivatives, you're basically going to give mod x minus alpha. Basically, you give the low order truncation of the polynomial p of x up to x minus alpha. Up to a degree, yes, we give this, this will be the sort of this equivalent, the modular elementary equivalent of the polynomial. This will exactly be R minus.
Smallest is the order of derivatives.
Huh? Yeah, so yes is, so you give low order derivatives is basically all derivatives, all less than s derivatives. So there will be one more parameter thrown into this one, which will basically be the number of derivatives. So s equals 1 will exactly be this setting. So it will be a strict generalization of the Reed-Solomon and the Reed-Muller world, in which if s equals 1, you recover the Reed-Solomon and the Reed-Muller. Okay.
So what is the alphabet of the?
Yeah, we will come to that. We will define the code in all its glory shortly. But before that, I should. Yeah. Okay. Let's look at a bit of history of this before I go into the formal treatment. So, to the theory community, as I mentioned, the multiplicity codes were first defined by Party, Shubhangi Saraf, and Sergey Akran, but actually there were coding in the coding community. These codes were at least the univariate counterparts were already discovered earlier, as early as 97. So, in 97, the n equals 1 case was Rosenblum and Fassman. So this is a paper in Russian. They actually introduced the univariate multiplicity code. So it was followed by, in 2001, also the n equals case by Nielsen. What he did was he actually took the Welch-Berlekamp algorithm that we saw and the Guruswamy-Sudan algorithms and showed that both these algorithms, which work for Reed-Solomon, also work for the univariate multiplicity. So, sort of extended Welch-Berlekamp and Guruswamy-Sudan algorithms to the univariate multiplicity setting. And then, a decade later, in 2011, the general n setting was introduced by Party, Saraf, and Yakhanen. So they defined the more general multiplicity code, and this was they did it in the context of the what they did it in the context of locally decodable codes with rate approaching 1. Previously, it was not able to do this. They use these new codes to actually get these. We'll see, depending on how much time we'll have, we'll see. This was immediately followed in 2012. Again, this was the n equals 1 case in which Party when Guruswamy and Wang they sort of showed that multiplicity codes were really univariate multiplicity codes. Nielsen had already observed that they were less decodable all the way up to the Johnson radius. He just extended the Reed-Solomon case. What they showed was actually it's not just the Johnson radius, it goes all the way to capacity. So this decodable all the way to capacity. This was not the first code that had this property. See, we were in search of explicit such codes. Just the previous year or something, Guruswamy and Rudra had come up with folded Reed-Solomon codes which achieve this property. And this is sort of, it was another code which has this property. What Kopati and Guruswamy Wang observed was they gave yet another code which explicitly achieved. Now we do know a family of, so we know that the random code achieves this decodable all the way up to capacity. And we do have a small set of explicit code which achieve capacity, but they all fall into the same class. They'll all be polynomial based codes like the Reed-Solomon code, the multiplicity code, there's the additive folded Reed-Solomon code, and there are several such codes which are, but they're all related to this. Only those codes we know which are achievable to the decoding of the capacity. Okay. And since then, there have been several other applications of these codes. They've been used for in combinatorial constructions and so. So what we will try to do is we'll start off in this lecture, give a formal definition of multiplicity codes and try to prove the Kopati and the Guruswamy Wang result. We won't be done. We'll have to defer large part of it to next lecture. And then see the Kopati Saraf-Yakkanen result, why these codes, the multivariate version of them, why are they locally decodable to rates approaching 1. We'll see those both, and then we'll see some application to combinatorics later on, depending on how much time. That will be the plan for the next 2 lectures. So let's begin with the formal treatment of my. Yeah, so multiplicity codes by almost a definition. They talk about we are going to be interested in the multiplicity at a point. How many times does the polynomial vanish at a particular point? Notice this is not a new concept to us. We have already seen this when we did the Guruswamy-Sudan algorithm. We introduced the notion of multiplicities. Typically, when you're working with over the reals and complexes, this notion of multiplicity is best captured using derivatives. But we did not do this when we did Guruswamy-Sudan. We completely skirted around the issue of derivatives. We just defined what it means for a point to vanish with multiplicity R. We didn't say the lower order derivatives all vanish. We just said that if a point vanishes with multiplicity R, this is what it means. We gave a definition of that and we work with that definition. And there's a reason for this. It's derivatives become messy over finite fields. We could do the same thing. We could completely skirt around the notion of derivatives, define everything in terms of multiplicities and do it. But given that we're going to spend so much time, let's actually be brave and go ahead and define we'll try to find out what are the issues with defining in terms of derivatives, using notion of derivatives. We'll find that there's some problems with defining derivatives, so we'll extend the notion of derivatives to finite fields. This will be what's called the Hasse derivatives, and then we'll define it in terms of Hasse. So this will be exact. We disconnected. Yeah, so what we'll do is we'll actually try to understand why the usual notion of derivative fails. Define. So we'll do the right honorable thing and we'll actually define Hasse derivatives and then define multiples. So first, let's look at let's do the real case firstly and see what the issue. So the reals or the complexes. What I want is the notion of derivatives is what we want to define. So let's look at the reals and complexes. But we are going to be talking of derivatives of only polynomials. In the reals and complexes, we can talk of derivatives and more in the limit world and all. We are not going. We are only going to be talking. All our functions will be polynomials or bounded to. The derivatives are very vanilla objects here. We don't need this. We don't need to be talking of polynomials. So suppose f of x was equal to x squared. What's its zero order derivative? Of course, that's right. So we would have, that would mean f of x is, f of the first order derivative will be 2x. The second order derivative will be 2. And subsequent derivatives will all be 0. This is how the usual notion of derivatives for this is. So that's an example. And what's one nice property with when you have these derivatives? You have this. The key thing to keep in mind is this Taylor series. The Taylor series is this infinite series approximation. This one, for the case of polynomials, is not an infinite series, just a finite series. One. So suppose you want to write f of alpha plus epsilon. How does the Taylor series go? It's sort of like f of alpha plus f prime of alpha times epsilon plus f double prime of alpha times epsilon squared by 2 and so on. In general, it will be the r the derivative epsilon per r, and you have r factorial. Right? So this is how we define. This is an object which we will repeatedly sort of. So if you want to take, for example, if you want, okay, let's keep this. Now, you could think of trying to do the same notion. So let's write what f of x squared and this. So for this particular thing, so alpha plus epsilon squared will be what? Will be alpha squared plus 2 alpha times epsilon plus 2 times epsilon squared by 2, which is the same as alpha squared plus 2 alpha epsilon plus epsilon squared. Yeah, I'm not doing anything fancy over there. That's what we all know. This is what Taylor series is another way. Okay. Now you could ask, can I define derivatives the same? Why can't I define in a finite field? Say for x squared, its first derivative be 2x. Its second derivative be f prime x to be 2. Now suppose we work, fair enough, let's see what happens if we do this. Let's work over a GF, over a field and with the characteristics, any one of the GF2 fields. What happens? Now both the derivative and the second derivative vanish because it's 2 and 2. But what is, so now let's look at what I want to say is, let's look at a GF2 field. If I had defined derivatives in that way, f of x, the same notion of derivative and just extended that, both the first order derivative and the second order derivative would have been 0. But what would be Taylor series? What would be the corresponding expression over here? I want alpha square plus epsilon square, but if I do Taylor series, I won't get the second order derivative is 0. So the point is there's a 1 by 2 factorial going on over there, which was defined over there. Because of the reals, you could divide by any number, you could do that. We can't do it. So even though it was 2 over there, that 1 by 2 came in, divided, take put away the 2, therefore, even though both the first order and the second order derivatives happen to be 0, some of them, the R factorial below, remove the reason for their being 0. Eliminated reason and they became non-zero when you're doing this. But some of them, like the first order derivative, continues to remain 0. The second order derivative is 1. So there's this mess with it. Firstly, you can't apply Taylor series because you are dividing by R factorial. You have to work, you can work only if the characteristic is large enough. So to avoid all of this, so to avoid all of this, what we will define derivatives is we'll define derivatives because we'll eventually be using sort of the Taylor approximation, Taylor series sort of thing. We'll define derivatives what Taylor is going to tell. That's how we'll define derivative, and that will be the. So that's one. So we're going to define. So this above definition doesn't extend. Does not extend. And the main problem, as we point out, is this division by r factorial might not be feasible. Okay. So it's not as if you can say first order derivative, second order, both are zero. You want one of them to be zero, you want the other one to be non-zero. You want the second order derivative to be zero. So what we will do is so this will be in terms of what are called Hasse derivatives. This sort of gets around this issue. So it gets around the issue. It has most properties of derivatives, but some properties, it won't have all the nice properties that we usually work with derivatives. We'll see them shortly. So I'm going to define it in more generality. We'll define it even for the multivariate version of the problem. So and we are only going to do this for polynomials. Derivatives of polynomials. In fact, I don't know how to do this otherwise. So that's only work for polynomials. Derivatives of polynomials. So we are going to be working more generally. M is the number of variables. And it will be convenient for me to write x bar, which is the set of variables x1 to xm. We'll use the bar notation to represent the vectors. And we'll be looking at monomials of the form x1 to the power e1, x2 to the power e2, all the way to xm to the power em. This we write it as short as x bar to the power e bar, where x bar is as before and e bar is this e1, e2.
Only the finite things.
Yeah, Hasse derivative finite. Hasse derivative and yet with some finite. If necessary, it's Hasse derivative to define it over anything. The definition works. It doesn't. So if it's not a finite field, you could use the usual notion of derivative. If it's not a finite field, or if the characteristic is larger than the degree of the polynomials we work with, it's best to actually work with the usual notion of derivatives because they have more properties than the Hasse derivatives. These will be almost, they will be scalars. Basically, this will be scalings of the usual notion of derivatives. It will be just the usual notion of derivatives multiplied by some scalar quantities to end this one. So it is almost the same notion. You see it in the sense. And because of the scalar, it inherits some properties, but not all properties of derivatives. Therefore, the finite field goes with characteristics say B. So I want to define the ith order. So I is some. I is so that I bar itself be a vector. I1, I2. Again, state it more generally. I want to define ith order derivative. Basically, we're going to define it such that Taylor series is true. So of the polynomial P of x. What was Taylor series? We took the polynomial x square. We wrote alpha plus epsilon square, expanded it out. The coefficient of alpha square was called the evaluation. The coefficient of epsilon, the constant was alpha square. The coefficient of the constant term in epsilon was the evaluation of alpha square. The coefficient of epsilon was the first. The first order derivative was the scaling of this quantity. The coefficient of epsilon square, scaling of that was the second order derivative. You will now define derivative just to be the corresponding coefficient. So we just write. I'm going to write P of x plus z. So take two formal polynomials, x and z are two formal polynomials, x1 to xn, z1 to zn. Now expand this guy out in the this one. So when you expand this one out, this will be some polynomial in, and just collect similar terms in z, just like we collected similar terms in epsilon over there. Let's collect similar terms in z. This will be accompanied by something. That something will be what I will call as the ith order. So you can write it in this form always.
I think you want to put E there.
I said ith order derivative, so.
So I is fixed, but the inner summation is in terms of E.
So the inner summation is important.
It is Z power E.
Z power E, yeah. Sorry. This should be P of. So you collect whatever is the coefficient of Z power E, that will be some polynomial in X, and that polynomial is what I will call the Hasse derivative.
So the I derivative is Pi of
Pi of X, where that is going to be.
So either second line E is equal to for pupils E.
Huh?
So I is also
I is also a tuple. So it's going to be the first derivative. So you, in fact, we'll be talking long order, not just the second derivative, third derivative. We'll talk about the first derivative with respect to x, the second derivative, we'll be talking about dou of x, dou square of f by dou x, dou y. We will be talking about all these higher order derivatives, mixed derivatives. So that's where you're going to get the i's. Okay, for the univariate, I is just a scalar quantity which is ranging between 0 all the way up to whatever the degree of the polynomial will be. So it's the most natural thing. This is exactly the same notion of derivative, except with the notion of derivative, they will give you the R factorial terms coming. Basically, you have incorporated the R factorial terms inside my derivative. Is that okay?
So the definition does not depend on
No. So I expand this guy out in this monomial base, in the monomial basis for E.
Yeah.
So I will be one such vector that appears in this. So I is also a vector. E is a different type of monomial. So it's the coefficient of that particular Z bar I. So let's take an example. Let's take an example. Let's just take.
No, I guess you just form the order of the definition. Right? I mean, you know that you can write P of x plus Z as the expression. That doesn't involve money.
Yeah, and then
So
the derivative of this one. So it's just, I'm just going to go back over here. Look at this thing over here. It's so the coefficient of the constant term was the 0th order derivative. The coefficient of epsilon was the first order derivative of this scaling. The coefficient of epsilon square was the second order derivative. We're going to take the same approach. The coefficient of Z power I will be the ith order. Okay. So P of x in this word. So what will be x plus z square? Is x square plus c square. So in particular, the 0 of x will be x square. P, the first order derivative will be 0, but the second order derivative will be 1. And that's important. But the way we defined it previously, this would have been also 0. I don't want that to happen. I want this to be 1 so that I can get the Taylor series. But I defined it as that Taylor series is 2. I turned the table around, I defined it as the Taylor series. Okay. So it's just a scaling of the usual notion of derivative to get around this R factorial problem that you have. Okay.
I guess the key point is that in standard derivative, once you become 0, you will end up staying 0.
You will say 0, this will not be 0. Because the standard function of derivative is defined as an iterative process. The third derivative is the first derivative of the second derivative. That's how we define the derivatives. That is, n, you just define one derivative and set the I plus first derivative is the derivative of the ith derivative. We are not defining it. The whole point is we don't want to define it iteratively because of this feature. That once it becomes 0, it will remain 0. I do want places where the first order derivative will be 0, but the second order derivative will be non-zero. And that's why I define the derivative, all of them together. I don't define it as an iterative process. And that's the key difference. So if you use this powerful thing of the iterative derivative notion which we had, and this one you could define with the take the third derivative and then take two more derivatives to get the fifth derivative. Here we don't. You'll see something that comes close to it, but we'll see that you don't get the fifth derivative. So it's not the definition is not an iterative definition. I just define. I tell you which derivative I want to get, and I just say it's the coefficient of the corresponding monomial in this expansion. It's basically just set so that the Taylor series, the Taylor approximation works. That's all. So Hasse derivatives is nothing fancy, it's just exactly what you want from the Taylor approximation. Let's see some properties of Hasse derivatives. What are some properties? So if you have the ith order derivative of a polynomial and the ith order derivative of another polynomial, I is a vector here. I'm not going to put vector over here. It's certainly the definition will tell you it's the ith order. It has the addition. You can add the polynomials. So that's not hard. Suppose I want to do this for the product. What would this be? It will basically be convolution. Yeah, it will be exactly convolution. You will have sum over all eth order exponents, where e is something less than or equal to I. That is all lower order things. You will have the eth order derivative of x times the I minus eth order derivative. What's the corresponding expression that you have for in the real world? The regular derivatives on the Hasse derivatives. There will be factorials coming up. So actually the product rule is nicer here than it was, and then you had these binomial coefficients that were coming up over here because of the iterative definition. Here the product rule is a cleaner rule. But the product rule becomes a nicer rule, but the thing that you lose is the iterated rule. So suppose I have the ith order derivative of this one, and then I go ahead and then take the jth order derivative. In the usual notion of derivatives, this will be I plus j choose. This will be the I plus j derivative of x. This is not going to be, open it out, this will be I plus j choose I, the derivative of jx. I have to define what I mean. In general, if I have two vectors, if I have where E bar choose F bar is defined as product of EI choose F. This. So the point is that the reason iterative definition is not true is that you can't divide by I plus j choose I. That might be 0. So that can't be used as a definition. It might be that iterative definition is 0. The iterated this one is 0, but yet this is non-zero. And that's not because of this, that's because of this binomial coefficient vanished, which didn't happen over fields of characteristic 0, but could potentially happen over fields of finite characteristics. Yeah, basically that's what happened. It's the thing that the product rule became nicer, the iterated rule became a. And we now define the notion of multiplicity. Multiplicity of a polynomial p at a point. So when you want to capture the fact that at the point alpha, the polynomial p goes to it, say some s times or r times. What does that mean in the other word? We said all derivatives of order less than r vanish. It's going to be exactly the same definition. This is what we will say. And notice, yeah, so what basically we will say that the multiplicity of the polynomial p at a will be the max over all r's in non-negative integers, such that PE of x is identically zero polynomial. Sorry, not the zero polynomial. PE at when evaluated at the point A is zero for all e's, such that the weight of E is less than R. And what do I mean by weight? Where weight of E, actually let me not use the term weight of E, but I want to just use mod E bar is just summation. This is exactly the same notion of this one. And notice that if this were indeed the case, what happens? Let's look at, suppose I have P of x plus C. What did we write it as? Summation PE of x Z. Now let's substitute x with A and Z with x minus B. What will we get? We get P of x equals summation PE at the point A, Z. Okay. Let's focus. Let's for now. All of this is true in this one. Let's just look at the univariate case to get a handle of it. Suppose mult PA equals R. That is, everything up to less than R vanished. What would, Z would have been? That is x minus A to the power. What would have happened here? What would happen? So all the lower order guys are zero. Every other term that you will have x minus A to the power E. So basically you will have that P of x will be some x minus A to the power R times some other polynomial Q of x, which basically says, so let's say the multiplicity of this is at least R. If it's at least R, this is what you have. That means P vanishes at least R times at the point. So it captures the exact notion. So previously we had, when we worked with Guruswami Sudan, we completely skirted around defining Hasse derivatives. We just defined multiplicity this way and didn't define Hasse derivatives, but this is just their equivalent way of defining multiplicity at that point. So you could also say, you could either say that how did we define it over there? We said at the point, we defined it at the origin. We said that P has multiplicity R at the origin. When you write it as a polynomial, you don't have any monomials whose total weight is less than R. That's what we wrote it as. And that is equivalent to the function. That's exactly what we are stating. Defining. So basically the Hasse, all I'm claiming over here, that is the Hasse notion of Hasse derivative definition of multiplicity coincides with the Guruswami Sudha notion that we had defined. Okay. Now formally defined. So a whole bunch of things. Suppose we're working with some field X. P, say with characteristic P. The M is going to be the number of variables. G will be the degree of the polynomial, this will be the degree parameter. Now we're going to have yet another parameter which is S, which is the multiplicity parameter. So this is a number and it's a non-negative, it's a positive integer. This is a non-negative integer. And S will also be a non-negative integer. It can be C. Sorry, S will be a S will not, S will always be positive. We'll talk of S being from 1 onwards, not from 0 onwards. So now it's going to be the same object. What we are going to do is we're going to interpret the polynomial as a degree, the message as the coefficient of the degree polynomial, and the evaluation as giving out for, and also you'll have a bunch of, so yes, N is the number of points of evaluation. The S is some alpha 1, alpha 2, alpha N, with this N distinct polynomials, N distinct points in the ambient space. What we're going to do is for each of these points, we are going to, the code is basically going to be, the multiplicity code is going to map the message polynomial into the evaluation of poly and the derivatives at alpha I, at alpha for alpha belongs to this. That's going to be the encoding map. That's going to be the encoding map. Let's spell it out a little more closely. So what will this be? So the message is set of all degree D polynomials. How many degree D polynomials are there? What is the number of, so the ambient dimension of the space will be the number of monomials of degree at most D in M variables. How much is this? M plus D, choose M. So this will, the message is going to take, it's going to map this. So it's going to take a polynomial this way, and it's going to map it to some alphabet sigma to the power n. Where this is where these questions come. What is sigma? Sigma is going to give me all the lower order multiplicities. So you want to give all multiplicities of less than S. So let's just first ask the univariate calculation. If you want to give all multiplicities less than S, how many things do you have to give me? How many field elements? You have to give the evaluation of the polynomial, the first order derivative, the second order derivative, all the way up to the S minus first order derivative. Yes. So in the case M equals 1, that is yes. And what about M equals 2? So for example, say S is 2. That means you have to give me the 0th order derivative. You all, so then you have to give 0th order derivative, the first order derivative next, the first order derivative in Y. No mixed derivatives, already the way it will cross. Suppose it's 3. You're going to give the first order derivative, the second order derivative next, the first order derivative in Y, the 0th order, the first order, the second order. Now the mixed terms you can give X, Y the derivative. First order next, first order Y. You will give that mixed derivative also. So these will all be different. How many of them will be there? So this will exactly going to be m plus s minus 1. Choose m. It's exactly the same thing. I want everything there with everything less than or equal to d. Here with everything less than or equal to s minus 1. So that's the. So notice this is a case in which the alphabet of the input and the alphabet of the output are not exactly the same alphabet. We are going to use the input as the string and the output alphabet. You can. The output alphabet is going to be this time. You're going to think of this as one single symbol. You're not going to think of the alphabet as f and giving n times this. That will be a different. That is just the evaluation of all these polynomials, but you don't correlate. I'm going to correlate. I'm going to club together the polynomial and all its derivatives together and give it as one single giant symbol at this location. So that's the response. We are going to map P is going to map to P of E bar at A for all E bar such that mod E is less than S, and this happened. That's the whole thing is one alphabet symbol, and I'm going to give this for every A in S. Those are the different. Huh?
How would we change it instead of fitting it all into the alphabet we were to have previously fit up? That's a trade-off.
Huh?
Fit in alphabet.
So yeah, it has an advantage is the alphabet becomes smaller. But the point is there are certain advantages of clubbing, and you see this in the proof, the way the proof happens. Knowing that this is correct tells you that it has an S order derivative. Suppose you know all, suppose it's just the same thing. Suppose you know that the evaluation is 0. That means you know you had it 0 at that point. So if a point was, if two things, let's look at it from the distance point of view. If you knew that P and Q agreed at a particular point, what did it mean in the usual S equals 1 case? It means at the point A, x minus alpha was the root of P minus Q. Let's once again work in the multiplicity word. Suppose at the point A, I know that the evaluation of P and Q agree. What would this mean? This means x minus alpha to the power s divides the difference between P minus Q. This will happen only if I club them together. If I don't club them together, I need them to agree not just at this location, I need them to agree at all these locations simultaneously, which is the same thing as saying I'm thinking of them as one single symbol. So basically, I want to get this extra power. When they agree, I don't want to get just that x minus alpha is the root of the difference polynomial. I want to get that x minus alpha to the power s is the root of the difference polynomial. Is a factor of the difference polynomial. Notice by now this should be of this. I will put it in short or in short. Represent this as P less than S A belongs. Okay, that's what I mean. Okay, notice this is also equivalent to, because of our this one, this is also equivalent to giving P of x mod x minus A to the power s. At least in the univariate world, this is what it means. In the univariate. Setting. In the multivariate setting also this can be generalized. This will just mean P of x mod the ideal x1 minus a1, x2 minus a2, all the way up to xn minus am, that whole ideal to the power s. That's what it means. Let's not go into that. That's what it will mean in the. So let's stick with the Hasse derivative.
This is slightly weird to insert that it has all the properties of a linear code.
So
It's not linear for a very weird reason.
it's not linear for a very weird reason, but the alphabet is not a field. Alphabet is not a field. Alphabet is a vector space. The alphabet is a vector space. Alphabet is f to the m plus s minus 1 choose here. So it's not a linear code and we want to got definition of linear code. So what we do is we protest that this not being called a linear code. We change the definition of linear code not only to give in which the output alphabet is not just f, but actually can give a vector space and then it will be linear over that field. Yeah, so it is not a linear code in the usual notion thing. It will be nice to see if there is, you can pack this as, use this as a giant field of appropriate thing and do it. But the point is, fields don't exist for all everything to yes. Fields exist only. No, you could use it power something. No, F power something, you could do it. No, even then it has to be F power. It can be anything, it can be anything.
Yeah, but the problem is multiplication by an element in this field. I don't know if there is a right polynomial such that these become the derivative.
So you will notice that multiplication is actually will be a convolution. That is, you take two things when you multiply them, what you have is convolution will happen. We will see, we will not do it this lecture, possibly the next lecture or something. Things will get mixed up. That is, you're going to take the dot product between two things, how you take the dot product. The point, anyway, so let me not do this, let me not go and define change the definition of linear. That's the definition of linear code. This is not linear code because linear code has this other thing was you could define a bilinear form. You could take one code word and take another code word, and you could talk about if you had one code word x1, x2, xn, another code word y1, y2, yn, you could talk a bilinear form, which is x1 dot y1 plus x2 dot y2. You could and you could do that multiplication because they were field elements. Now you can't do that multiplication. You have a vector here, you have a vector here. How are you going to do it? You'll have to now define a multiplication process between it to define a bilinear form. We can do all of that. You can define a suitable bilinear form for multiplicity codes such that multiplicity codes are their own dual. You can do everything. All the nice properties of rate color and rate Muller extend this to in a very, very clean fashion. You can, things work out perfectly. These are super nice objects. We will only define as much as we need for our particular application. We want to go. There are a lot of interesting and open questions with respect to these codes. Yeah. Okay. So that's any questions on the definition? Quite a word. So, the definition, it's the most natural generalization of okay. So let's go ahead and ask some more property. The rate of this code, we are not going to write rate of. So you can write rate of this code, but you know we can write rate of this code, the dimension and all of this. You have the dimension, the block length. You can write the rate of the code. I'm not going to write rate of the code. What we will, because typically when you write rate, we always assume we wrote it as k by n, but this was under the assumption that the input alphabet and the output alphabet were the same. But here they are not. Therefore, then you should write it not as k by n, you should write as a block length by log f, by the number of log of the number of code words by n. That's what you should write it. And if you write it, you can get the right. So it will be basically, it will be, what will it be? It will be d plus m choose. It will be a nasty object. I will not want to write this rate. You can write it. Rate, you can define it totally. What will be more interesting is this course. Yeah, actually, what we will do now, so we define multiplicity code very generally for any the M-variate thing. For the rest of the lecture, we will focus on the M equal one. So we will focus. We'll come back to the higher multiplication. Okay, so that's the lecture. focus on univariate. And equals 1. Multiplicity. So what was the corresponding notion that we used to understand the existence of the Reed-Solomon code, the univariate corresponding univariate? Yeah, how many times can the polynomial be zero? We'll ask exactly the same question here. We'll ask, suppose P is not the identically zero polynomial. And the degree of P is say less than equal to T. Some degree T polynomial. What I'm going to ask is, what is the probability that when I pick a random point in S, and S is some collection of alpha 1 to alpha something, some collection of P. I want the entire lower order derivative P less than S, A to be equal to 0. This is equivalent to stating that probability A less than S, then the multiplicity of P at A is greater than or equal to S. That's exactly the same notion. What's this probability? How many points can there be such that when I pick a random point from 1 to n, such that it vanishes with multiplicity yes at that point? Yeah, so sum of the multiplicities of each of them is bounded by t. Therefore, in particular, this would say that the number of, suppose there are k such points for which this is case, k times yes should be less than t. In particular, we are going to get the following. This will exactly be, this will be less than or equal to d times yes over n. Because each time it is 0, it eats a factor of yes. So notice that this is, and this is the key take reason multiplicity codes are slightly better. You thought that Reed-Solomon code had a good, very good distance. They had distance d over n, and you could make that this one. These are distance even better than it because you're going to get yes to be even larger. Therefore, the probability that they are actually equal is going to become even smaller than what we had. Therefore, in other words, this will be. What sense do you mean? It cannot be greater than the singleton ball. In that sense, it's not. It's the fact that when you are working with a degree D polynomial, because you allow this larger aspect, of course, you can't compare rate polynomial with multivariate multiplicity. They're apples and oranges. We're giving more information at this point. But I think if you look at the same degree D polynomial over here, I can get distance even better, even closer to 1 than what I would have got with the product. Yeah. And we will immediately see that actually we just right now see that you actually have done this in your problem set. The multiplicity could be univariate multiplicity code. So the problem, the first or second problem set. And you showed actually it's an MDS code. And we'll actually see a easy example. We'll see why that's true. So, but immediate consequence of this is the following. The consequence of this is the distance of univariate multiplicity is at least 1 minus d by s. That's how much they can agree, therefore it's at least much.
An alternate way to interpret this is like if you were forced to work with a degree D polynomial as your message. In order for you to have gotten any distance in the univariate setting, you would be forced to choose n to be bigger than this. Because otherwise d over n would not even have been less than 1.
Yeah.
But in the multiplicity setting, you can afford to work with a fewer points. If you can instead pay for it by making s a little.
Yeah, so what's going to, yeah, so we will see this better. What Prahladh is trying to say is, what was one of the big caveats of the Solomon code, where you needed that if you're working with degree D, you needed n points of evaluation. If you work with degree D, you at least need d points of evaluation, because d by n has to be a number less than or equal to 1. And in fact, to get code distance, you needed the number of evaluation points to be at least b. Now you can ask the same question: do I need the same thing over here? So let's work with your multiplicity 2. What I would need here is b to be less than 2n, not b to be less than n. So you can actually interpret. Previously, we were forced to work with just suppose you had n points of this one. The message could be only anything of f to the power some k, where k is less than n. Now, if you're going for multiplicity 2, the message could go all the way to f to the 2k, and yet you could do, of course, it comes at a price. You're going to give more information at every location. You're also going to give the second order derivative, but it lets you encode the message. It lets you take even larger degree polynomial. Particularly, we will probably looking at polynomials whose degree is actually larger than the field size. We look at polynomials which are, say, you're working on a prime field Q. We'll be looking at polynomials which are degree like 1.5 cube and all of this. See, in the Reed-Solomon case, we could not do this. The degree of the polynomial had to be only smaller. Because only the evaluation mattered. If you were looking at the evaluation, there's no point of going degree more than the field size. Here, the evaluation and the derivatives matter. So you can in principle look at polynomials. So the polynomial is viewed as a syntactic object. It's just a list of coefficients of this object. And in principle, you can look at polynomials whose degrees are much larger than the field size. In fact, that's where we get all our advantage, both in the capacity question and in the, it will be even more evident in the local decoding question from next time. And I want to state that just the rate of it, people write the rate of it this way, the rate of univariate multiplicity. So it's usually written as n times d plus 1n. So there are d plus 1 field elements the message has. The output has n also field elements. Therefore, there's d plus 1 field elements are being smeared across Sn field elements. So then this is the sort of rate of comparing then the same quantity in numerator. That's the rate of the code. And notice that this satisfies it beats the singleton code. It beats the singleton code. So therefore, this is also it's an MDS. That's the best you can get. Distance is not just that; it is exactly that. So we might just the code. Or achieve. Singleton from. And equivalent ways, a nice thing about MDS codes is you give me the location at any certain number of places. They will always, as long as the number of places is not more than the rate of this one, you always have a polynomial that takes that particular at any set of location. And basically, one way of to do this is write a Lagrange interpolation. Say that there is a polynomial which exactly takes this one. And you can do exactly the same thing over here. You can suppose I give you that at A1, A2, AN, each of these places, P less than S of AI. Rather, I'm going to give it as I'm going to give that P of X mod x minus bi. I tell it is the polynomial. I give it the polynomial Ri of x. And tell you xi to the power s. So at the location ai, it is this particular. I give you this polynomial. So I can. So how does suppose I just gave you the information Ris. So so this tells you from P you can create the Ris. I want to say from Ris you can recover this one. What will that be? That will exactly be P of x will have to be this object. It will be summation over A in S Ri of x mod x minus b to the power s b not b in s minus a by a minus b to the power s. So exactly the same. That is, s was 1 in the usual Lagrange interpolator, so that was larger than 1. You can interpolate it. To give me any sort of point, they will, if you know the evaluation system, you can find the unique polynomial one, and this works. Okay. So now let's get on to the next question. Now that we have, it's also a fantastic code like the Reed-Solomon code. We can very quantitative achieve the physical form. Question is now, can we also get efficient decoding algorithms for it? So now we'll turn to the question of decoding algorithms for univariate multiple. That will be the topic. We spend possibly the next, the rest of this lecture with another 5-10 minutes and most of the next lecture. We can ask several questions here. Firstly, we can ask decoding up to. So firstly, we can ask unique decoding. And this is up to half the minimum distance. That is half of 1 minus e by xn. We ask this question. 2, we ask list decoding up to the Johnson radius. And what did we see? At least in the Reed-Solomon case, we had the Welsh-Berlekamp algorithm for the first and the Monsoon algorithm for one. And basically, as I mentioned at the beginning of the lecture, Nielsen has basically shown that both these algorithms, when written correctly in the context of multiplicity codes, just work. And actually, so basically, we just say that it needs to be checked. So, Welsh-Berlekamp and Monsoon generalize. And this is generalize in the most natural fashion. So what we'll do, we'll actually not do this. We already had explicit code which are list decodable up to half the minimum distance, although Johnson radius, we saw that. Okay. Question is more important here is list decoding beyond the Johnson. So, and this was actually answered. So, Swastik, Kaparti, and independently Guruswamy and Van showed that multiplicity codes are list decodable beyond the operator, in fact, all the way up to distance. State this in a slightly distance or capacity. Stated this carefully. It's not that all multiplicity codes are achieved. In the case of Reed-Solomon, every Reed-Solomon code was list decodable all the way up to Johnson radius. You tell me how close to capacity you want to achieve. I will tell you what is the multiplicity parameter you have to choose so that it will be a constant. If you want to get epsilon close to capacity, I will give you a multiplicity parameter, which is a function of epsilon. And that corresponding multiplicity code will be list decodable up to capacity. That's what we get. Because otherwise, if we prove this result, it means read solvent is list decodable, because read solvent is just a special case of multiplicity codes. If they say multiplicity codes are list decodable all the way up to capacity, in particular, that means read solvable codes are also list decodable up to capacity. That's not what we will prove. We'll say tell me how close you want to come to capacity. Based on that, I will give you an S, which is large enough but a constant, so that the corresponding multiplicity. So this rules out read solvent out of the picture. It will work only for S's large enough. It says the multiplicity code with multiplicity at least that S of epsilon will be list decodable. So what?
Even the alphabet size could depend on this gap.
Hmm?
Even the alphabet size gives it depend on this gap.
The alphabet size, because it's the multiplicity parameter, the alphabet size is going to go, because alphabet is f to the power m plus s minus 1 choose. M so it's included in it. Yeah. So the property and the uniform event, this is what they will show. For all epsilon, there exists a S, which is an S epsilon. There is S, which is S naught, such that multiplicity with what are the parameters? F, this is M equals 1. S being anything larger than S naught. DBD. Yes. List decodable. Till 1 minus D by Sn minus X. Up to that rate. Basically, you can go all the way. That's what you get. The DB parameter, that's the number of evaluation. Third that it will get you this decodable. We wanted to get into the gut source. So what we will do in lecture is the following. In lecture, these properties. But when I mean this decoding, I mean their efficiency. We will do this. It will be basically the idea will be we'll take the Goswami Sudan algorithm and we now try to fit it into this. We just see what should be done. And it will take us some work to set the stage. But once that is done, it just works. Amazingly, and that's what we will do. Thought I will start it off this one, but I think it's too late. Let's because otherwise we'll do something and break it, and then when there's one, I had an intermediate midpoint in which I want to break, but we are far from that. So let's stop right now. This will be a in Wednesday's lecture. We will see properties. Let's do it. And so the problem that will go out today. The Gulfam Van algorithm, they did it for multiplicity codes. So basically, I will give additive FRS, which is not available in the moment, as one of the problems in the problems. We have to modify the Gulfam Van algorithm for additive FRS. That will be part of it. That's it.
So,
Yeah.
we say the capacity, capacity of a code is 1 minus 7.
No, it's 1 minus distance. So it's distance minus epsilon. Yeah.
So, for example, I could artificially construct an inequality code which by itself is very parts. In that case, in really this decoding there should be less.
So whenever we mean these, we don't mean a single code. We always mean a family.
On the DB file,
Not even the GV curve. These codes are better than these are not on the GV curve. So I don't even mean this. I just mean a family of codes. Family of codes for which I can recover, which have good rate and which are recoverable up to delta minus epsilon.
Okay, so what density you define it to be different.
Delta, because beyond delta, you can show that. So if the code goes beyond, if what you can show is the code has distance delta. If you go beyond delta, at least for MDS codes, right now, all the codes for which you'll be showing this will be MDS. For MDS, delta is 1 minus R. If you go beyond 1 minus R, you can show that they are received words which have exponentially, which have as many code words as the, not exponentially many, the number of words surrounding a point will be basically the size of the code. Yeah. So you basically come to the, say that, and here we will actually say in this case it will be much smaller. It will be polynomially smaller. In fact, what we will shortly see is it will not just be polynomially smaller. The proof which we will give will be a polynomial list. Actually, the list can be even truncated and you will get a constant size list. Even all the way to delta minus epsilon, the list will be just a constant dependent on epsilon. It won't.
My source of confusion was that if since beyond delta, you will always get exponentially many code words, but that is not true
If the code is fast, basically it will be comparable to the code word set. Yeah, it will be comparable.